Steady state error. Steady state error is a very interesting topic in control systems. I say so because students, rightly so, don't like memorizing anything for the exam. The exam itself is overwhelming, 5 hours and 20 minutes, 110 questions. Even with the reference handbook provided to you, the time it takes for you to actually maybe sometimes arrive at an equation, maybe sometimes go to the right section, and sometimes even just to understand what the question is asking for can be draining. Okay. Steady state error is one of those topics where you have to recognize that despite the fact that there is an entire table provided in the reference handbook, okay, under instrumentation and controls, I believe, right? Instrumentation, measurement, and controls. Yeah. And it is titled as steady state error. It is not the best way to approach it. Do you guys agree with me or not? Because if you have a surface level understanding of steady state errors, you haven't done much practice problems, let alone gone through a derivation, and you find yourself being asked steady state error question on the exam, 90% of the students are going to do a control F, type steady state error. And maybe after a couple of hits, you're going to land under instrumentation, measurement, and control. There is a nice, good looking table titled as steady state error. Agreed? Do you guys see yourself doing that? If you had little to no knowledge of steady state errors and have not invested time and effort during exam preparation, I think I would find myself in that situation. Now, the issue with that table is multifold. Number one, it's not very intuitive. It seems like it's just 1 divided by kb plus 1, and you go ahead and, plug and chug. First of all, the way that the table is presented, the reference handbook uses k for all inputs. And this is sort of a subtle detail. When we go through the derivation, which I have done for each and every one of them in the course, you recognize that this constant kp is different from kv and kv is different from ka. One is position, one is velocity, and the other one is acceleration. But even with this, figuring out the system type can be challenging. The table makes it sound and look as if it's just one simple calculation, but it's not. So my recommendation is to actually go a little bit around it. Okay. And this is where students feel a little bit uncomfortable sometimes. Like, why can't I just simply use the table? Go ahead and use the table after you've gone through those derivations and have an understanding of classifying the system type, which itself requires a little bit of manipulation of your transfer function, and it is not really mentioned very clearly in here. There's a formula just above the table that has kp divided by kb divided by s to the power of t, and that's the t. That is the t that tells you what is the system type. But for you to set it up like that, it can be a little bit challenging. Now, my recommendation when it comes to steady state error is to use a finite value theorem. And that's what the student is asking. I was trying to find final value theorem, not finite, final value theorem in the FE manual for the problems, but I can't seem to find it. Is it a formula that I must memorize? First of all, the FVT, the final value theorem, is given in the reference handbook. Where can you guys find it? It is part of the Laplace transform table. Okay. In the on-demand course, in the homework assignment, we've done some practice problems around it. So what is the gist of the final value theorem? It is very interesting. What it says is that if you're trying to find the error in steady state, what is the error in steady state? Very simply, let us assume that you have a target output value. Okay. You have a target output value, which is indicated by this blue line. And what you are able to achieve is this red line. And it can fluctuate about this mean value and whatnot. This delta over here in the time domain between the two, are you guys following me? Okay. During steady state conditions is your steady state error in the time domain. So the blue line is where you want to be. The red is what you are achieving. And during normal operating conditions, during steady state, the difference between the two is our error function. The interesting thing about FVT, Final Value Theorem, is that it allows us to figure out a fixed quantity of a value, a precise value of this function e of t as time approaches infinity. Because steady state is that constant state, right? And you want it to have settled, right? When there are gyrations and volatility and whatnot, because of transients and disturbances and changes and whatnot. At time t is equal to infinity, or as t approaches infinity, you'd assume that things would have settled, right? It's a very beautiful equation because as time is approaching infinity, we are looking at the value of e of t. Now, let alone figuring out the value of a function at infinity, if you think about it, we ourselves cannot quantify what infinity is. At what time are you talking about infinity? What is infinity? Extremely large number. Okay. And at that extremely large number, we are figuring out the value of this error function. It's kind of mind boggling. We are able to achieve it though very simply by making use of this theorem, by stepping out of the time domain and into the Laplace or the S domain. So for this e of t, if I can find its Laplace transform, which is e of s, and e of s for this type of a control system, it is simply r of s, which is the input, divided by 1 plus g of s. And if you have gone through the derivation of the classical negative feedback control system, which I have recommended several times in the course, it is super easy to go from this block diagram to this. Okay? Make sense? So all you're doing is you're multiplying s with r of s divided by 1 plus g of s, and then setting s to 0. This will work regardless of the system type, regardless of the inputs, and you won't have to do anything extra. R of s is your input, the Laplace of the input, okay? And this is the derivation that I go through, right? If I define E of s as the difference between R of s, so this is my R of s that is coming in. You can quickly review this, and we've done a lot of these in the course. So if this is the E of s, you can see E of s input is R of s. I am subtracting Y of s. So E of s is simply equal to R of s minus Y of s. Okay. And if I look at this path, this trajectory, E of s is simply being multiplied with G of s, and it is giving me Y of s. So Y of s is simply equal to E of s times G of s, right? I am going to substitute E of s in here because it's this value, and I end up with this. I rearrange the equation. Okay, actually the right-hand side is Y of s. I rearrange the equation, and then I end up with Y of s is equal to R of s divided by 1 plus G of s. Okay. So I strongly recommend you to actually go through the final value theorem. Plenty of practice problems in the course. Recognize what it is doing for you. in the time domain, it is figuring out the value of the error function at infinity, which is called the steady state error. All you have to do is simply multiply s with r of s divided by 1 plus g of s. G of s is the s domain representation of whatever is in the block. And we've done several practice problems. G of s can take this form, s divided by s squared plus 1. Okay, it can be 1 divided by s plus 2. It can be whatever s domain representation of this block is. Okay, and then set s to 0. That's my recommendation. It's a surefire way of solving the steady state error problems. You can use the table that is in the reference handbook, but that requires you to figure out the types, and which I explained in the on-demand, but it requires a little bit extra work. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE Electrical and PE Power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE Electrical and PE Power exam preparation programs, please visit my website, studyforfe.com.